Okay, so we've now defined the idea of a vector valued function. So we've got this sort of hypothetical idea that you could have, some particle that's position depends on time, right? So a good example of that is I say I have a little fly, and the fly is flying around in space. So if I ask the question, where is this fly located? Well, its position at one time, r at t naught, is over here. Later on, it's located here. Later on, it's located there, right? So I could certainly imagine talking about the position of the fly as a function of time. Now, you're familiar with the idea that velocity is the time derivative of position, right? So if the fly is moving around in time, the velocity should be what the derivative is of that position. And so the question is, how do we actually do this? Well, you're probably used to doing this in Cartesian coordinates, but let's give an example of doing that in Cartesian coordinates. So we'll talk about Cartesian first, and let's just make something up. So r of t, let's come up with a kind of an obvious example, is cosine of t times I hat plus sine of t times j hat, right? So there's an example of a position vector that depends on time, right? It's got an x component that depends on time and a y component that depends on time. If we think about what that actually will look like, well, at t equals 0, cosine of 0 is 1, sine of 0 is 0. So at t equals 0, the phi will be located there. By the time that time advances to pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. So the fly will have moved to here, and so on. So this fly is happily flying around the unit circle, and it's completing one lap of the unit circle every 2 pi seconds. I will note that I've been pretty sloppy with regard to my units here. I, of course, should say that this is like 1 meter times cosine of t and 1 meter times sine of t, so that my position is actually as units of meters. Okay, so how do I find the velocity of the fly? Well, qualitatively, it's fairly easy to think about what the velocity of the fly is going to be. The velocity of the fly in this case is as how is it that r is changing. So right now, my r position is there. A little while later, the fly will be located there. And so the velocity is what the change in that position is over time. So the velocity should be pointing up, right? So graphically, it's basically v new minus v old, right? The change in the velocity divided by delta t. Should look familiar. It looks sort of like the definition of the derivative. And mathematically, it's something very similar. We're going to take the derivative with respect to time of the function cosine t I hat plus sine t j hat, and then I've got a 1 meter out front. Well, the time derivative of cosine t is what? I believe it's negative sine. The time derivative of sine t is plus cosine. And I hat and j hat aren't changing in time, right? They're constant unit vectors, and I sort of just did that without saying anything about it. But when I take this derivative, I'm actually taking derivative of cosine of t times I hat. I would use product rule for that, and derivative of cosine of t is minus sine of t times I hat. Derivative of I hat is 0 because it's not changing, so that drops out, and so on. So I end up getting a velocity that's 1 meter per second times this quantity. Okay? And if we check that, that does indeed make sense. When t equals 0, the fly is moving up. If I think about how fast the fly is moving at that point, the magnitude of the fly's velocity is 1 meter per second. Since the circle has a radius of 1, the length of that circle is 2 pi, so it will indeed take 2 pi seconds for the fly to go all the way around the circle. Okay? So that's an example of how you actually find a velocity in Cartesian coordinates by taking a derivative. Let's next move on to taking to figuring out a velocity in polar coordinates, and as we'll see, that's going to get a little bit more interesting.